Welcome to this module. This module is going to be talking about the population of the NASIS database. And what we're going to be discussing here is the precision, the accuracy, and the uncertainty of the data that you populate. Now, first thing that we need to consider is the databases that you're using. And there are three databases that you basically populate and collect your data from, and one's NASIS. And you need to understand that NASIS is an estimated properties database. What you're doing is you're estimating the soil properties, a low, an RV, and a high, for those soil properties within a component based off that component's population. Okay. And then the PEDON database, it once again is an estimated properties database, and you're estimating those properties based on that specific point. We'll go into more details on that, but it's estimated. And then, of course, KSSL is where you guys send your samples to have those analyzed. And the KSSL has the PEDON description in NASIS, and then they populate their LIMS database with their analyzed set of data, and then of course it goes out to the repository, the lab repository, and is available for you to use in NASIS and the Access database and on the web. So you've got quite a bit of data available to you, but you need to understand the differences in the databases. NASIS is estimated, your PEDONs are estimated, your KSSL is analyzed. Let's deviate just a little bit and talk about site selection. And I want to bring this point in reference to a soil survey area. We're going to look at a soil survey area. It's about 360,000 acres. Let's just assume that. And then let's also assume that we have a soil map unit that has an acreage of about 16,000 acres. So when you look at the number of polygons for that particular soil map unit within that survey area, it's about 500 polygons. So you have 500 individuals that are within the confines of that map unit for the survey area. And that population of the individuals averages out to about 32 acres per individual. And then when you look at the 16,000 acres of the map unit acreage, divide that by the polygons, it gets you the average acres per polygon. And when you consider what percentage that makes up, that's about 0.2% of the entire survey area. All right? So you're going to be making estimates on a map unit that represents 0.2% of the entire survey area. So when you stop and you think about all the map units that you've still got more than 99% more map units. They all have to be, you have to collect data on those. And most of the ways that we collect data is we describe a PEDON. And the generic sense of a PEDON is it's 1 cubic meter. So let's assume that we've got a surface area of 1 square meter. And if we do that, then the assumption is that that equals 0.00023 acres. That doesn't mean much for that entire survey area. So that 1 square meter is only about 0.007% of a delineation of a population, of an individual. And then that 1 square meter only equals to about 0.00014% of the entire soil map unit. So each one of those PEDONs that you write a description on or that you collect data on is only 0.00014% of the total acreage of the entire soil map unit, not the component, just the soil map unit. And then when you consider the fact that you don't look at that whole square meter unless you dig a pit. You typically look at an auger, and that auger is about 6 centimeters. It's about 4% of a square meter. So now you have narrowed down your vision of that population down to 6 times 10 to the minus 8% of the entire soil map unit. So you're making an estimate. You're populating estimated soil properties based on the number of PEDONs that you described using an auger hole that's only 6 times 10 to the minus 8% of the entire soil map unit. So I want you to keep that in mind as we discuss the soil properties that you're populating. So, you need to make sure that the selection of the site is important, because you want to make sure that you get something that represents what your vision of this particular component and this particular map unit actually is. And then when you think about how many points do I actually need to collect? Well, here's a county about 380,000 acres, and it's got about 3,600 pedons that have been described, but just been described, not sampled, just described. And when you look at that, that's you think, my God, that's a lot of pedons in an entire county. And it was, but when you look at that map and you see the way the transects are distributed, and you see the way the points are distributed, you see that there's holes in this map that were not, data was not collected. So we're having to make a lot of interpolation or extrapolation based off of other known areas. It's the reason why we have the way we map, is we map off a landform-based model. So let's get into the data. Let's talk about this data that you're collecting. You spend a lot of time gathering data, and you select point data, and you usually select point data to identify a soil series. And then you run transects, and you use those transects to estimate composition. And those textures that you're putting on that 232 form, those are going to hopefully be used to identify the PSD. So you want to be able to identify what the sand, silt, and clay is off of that texture. And the only way you're going to do that is if you give me at least 2 of those 3 points. And then you have the lab analysis. If you go in there and you collect lab data and you send that into KSSL, you then have that set of data to be able to use it. But I want you to understand that what you're doing is you're collecting field estimates, and you're collecting lab analysis, whether that lab analysis is done in your office or whether it's done at KSSL. You're now collecting multiple sets of different types of data, and you're going to analyze that information to be able to populate your component. So let's talk about this data collection. We collect and we take this data, and we also have all of this raw data at our disposal. Might be old 232s, might be your 232s, it might be old lab data, it might be new lab data, but it's raw data. And all this raw data has to be combined, has to be coalesced, has to be pulled together, and it has to be analyzed. And after that analysis, you then have to make decisions on how you're going to present this data to the public. So the first piece of data collection that we have to look at is uncertainty. And all lab data has uncertainty. And to give you an example of what is uncertainty, everybody assumes that the human temperature is 98.6 degrees. That's normal. So if you took 5 different thermometers and you measured a person's temperature with those 5 different thermometers, what would be the uncertainty? And so this statement of your body temperature, it indicates the measured value that you are associating with my body temperature or your body temperature, and the uncertainty in which that temperature exists. And when you look at that, you basically dependent, it could very well be that they're all going to come out with different temperatures, and you'll end up saying that it's 98.6 plus or minus a half a degree. So that gives you your range of being anything between 98.1 to 99.1. So that's your level of uncertainty based off your instrument. So I basically just mentioned that. The uncertainty of the measurement is determined by the device and the scale of that measuring device. It's also an amount of the variation that you're going to find in that measured value. And it does not imply that there's a mistake. It only implies that there's a natural spread of these values based off of that device and the scale of that device. And you can relate this back to your fingers when you're texturing. What's the uncertainty of estimating clay content when you're an experienced soil scientist? Is it 3%? Is it 5%? Or is it 10%? And the more experience you have in a certain area, the less uncertainty you have. So think about this as we think about all the other types of data we collect. What's the level of uncertainty in, let's say, your map unit composition? I could go back to that map and I could show you that map. A lot of the transects were run down the road. What's the level of uncertainty on something like that when they weren't, when the site selection wasn't biased enough to be able to give you the information necessary for what you feel is the heart of that map unit? And then what about pH? You all use pH kits, and you got to look at the uncertainty of the measurement and the scale. Well, when you're out taking pH in the field, you're only basing it off of 0.5%. And then you're basing it off of a color. And then you have to look at how good is your eye picking out that color code. A lot of uncertainty there. Look at clay content. The clay content. Is it clay content based on what you textured or based off what I textured? Is it the clay content based off what we ran in the hydrometer in our field lab or the pipette that we ran in the KSSL lab? A lot of uncertainty there. What about the organic matter content? You look at organic matter content, and did you estimate it, just ocular estimate? Did we use the old method? Keep in mind, I realize uncertainty is a single measurement and a single scale, but you got to look at all the different levels of uncertainty on all of this data that we have. Different measurements, different scales. That's uncertainty. And I'm uncertain about a lot of the data that's in the database. But let's move on. Let's talk about precision. Now, precision is a measure of how closely a group of the measurements agree with one another. And how close are those measurements to one another? How easily can they be reproduced? And they are a measure of the agreement of the experimental measurements with each other. What is the range and what is the standard deviation from it? And hopefully that close agreement translates into a small uncertainty. But even though you might be precise, it doesn't mean that those measurements are close to the true value. And what we have to determine is, what is the true value? Well, we always use these bullseye targets to be able to explain this. And I realize some of you probably know this, some of you probably don't. But if you look at the lower left-hand corner target, you'll see that those are pretty precise. Every one of those are grouped really close together. Unfortunately, they're not accurate. And the reason, you look around on all these other ones, you can see what it says, not accurate, not precise, and what's accurate and what's precise. All the bullets fall within a small area. And so we have small uncertainty within this area. But it certainly isn't accurate. So you can see that's where our true value is, but that's where our bullets are going through. So consider the precision of a sand, silt, and clay values that you collect. And what I hope is that as we move back into MLRA updates, that any data that's collected on a 232, there's going to be an estimate of the clay content and at least an estimate of the sand or the silt, so that you guys will have, a good field texture estimate that you need. And then you're also going to be taking samples and bringing them into your field lab, and you're going to be using your hydrometer method. And hopefully, through a lot of the analysis evaluations we've already done, there should be a dire need to send in samples to the KSSL and get the pipette method run, so that you now have these three different types of estimates. And so then you have to determine which one of these three methods that you're using has the greatest precision. Now, perfect example here is if we had 10 soil scientists and those 10 soil scientists were all texturing a sample, we could get 10 different values that were, for the clay content. And if we send it to KSSL and we have those 10 samples, you notice that there would be a significant difference in the sampling and in the precision of the way we've analyzed that data. So take a look at this and you think, okay, precision. What is the most precise method? Well, obviously it's the lab. That's the reason why we send stuff in for the lab for analysis. Okay, now which method has the greatest uncertainty? Let's just take that one person who's texturing and texturing and texturing, and let's take that one sample going to the lab and being run over and over and over. Which one is going to have the greatest uncertainty in it? And as you can guess, it's probably most likely going to be the soil scientist in the field texturing method. It's going to have the greatest uncertainty. So we've talked about uncertainty, we've talked about precision, now let's talk about accuracy. And this is how close we are to the true value. And we use this measure of standard deviation to be able to identify our percent error, which is from the true or the accepted value. Once again, we're going to return to the bullseye. We're going to take a look at this bullseye and we're going to say, okay, what does it say about the measurements? And obviously, for accuracy, we're wanting the bullseye. For precision, we're wanting the grouping around that bullseye. And so you can use this as a image to be able to identify what we're shooting for. We're trying to shoot for lab data, or for data that is the most accurate and the most precise and has the least amount of uncertainty. Unfortunately, you don't have that in the NASA's database because the NASA's database is built off of estimates. So what is the true value when you look at this? Is it the field sample? Is it the lab that's in the field office? Or is it the lab that's using the pipette method? And the true value that's accepted by our NCSS standards is that lab data that's confirmed at the KSSL. So, what can you say about the accuracy of the soil scientists and when they hand texture these estimates? How accurate are you at identifying that texture? How accurate are you at identifying the clay content? How accurate are you at identifying the sand or the silt content, whichever one you choose? Because each one of those hand-textured clay percentages, those guesses that you use, they represent an attempt to hit the bullseye, and that bullseye is the lab result. So then go back and say and look at this again, and you can see that one on the left-hand side we've got only integers, and if you're really good, you might get 3% plus or minus. And then if you look at the lab data on the right, when you look at this, you're seeing that they're all 23, and it's all plus or minus 0.1. Significant difference in the precision, the accuracy, and the uncertainty between the two sets of data. Now then, you're left with a dilemma here, because you've got three different sets of data coming together, and you have to analyze those three sets of data, and you have to look at the uncertainties, and you have to combine those uncertainties. And the rule is that you can only report out the lowest level of uncertainty. Keep that in mind because you're going to see some data here now. Let's compare the PET-ON data, where you've estimated the clay content, to the KSSL data, where you have actually gone in there and had them measure that. And notice the level of uncertainty. Your estimate's probably within plus or minus 3%. Their level of uncertainty is probably within 0.5%. And the precision and the accuracy, and you can look at this and just see the estimated clay contents and run up and down the columns, and you can see that somebody did a pretty good job estimating, but they're still not as precise and not as accurate. So that was point data. Now you have to aggregate that point data to a component. And once you've got it up to a component, keep in mind, we're using lab data from KSSL. We're probably using lab data from the field. And we're using the estimated field properties that you textured. So you have to use the lowest level of uncertainty. And of course, you're going to do a lot of analysis here, and you're going to make a lot of guesses as far as some of the missing data. But the point here is you're going to analyze many of these properties together. You're going to come up with an average of your estimated silts and estimated clays, and you're going to come up with an average of the silt total PSA and the clay total PSA. But when it all said and done, you have to take the lowest level of uncertainty when you populate. And the case in point here, notice they populated 34.3%. That is a lot of precision in an estimated database. We allow that that point to be in that field, but that is an improper population of that particular set of information. That does not represent the lowest level of uncertainty. So be aware of that. Do not populate lab data or the precision and accuracy of a lab data into the NASIS database. Just because we give you a decimal point does not mean you are correct in using it. So be very careful about that. That is an inappropriate use of the field right there. Those should have all been rounded to the integer. Now then, let's take a look at mapping and composition. We've got an example here, and we've got 56% and we got 31%. The 7 and the 6 I don't worry about too much. But let's take a look and let's put this in the relationship between uncertainty, precision, and accuracy. What's your uncertainty whenever you run transects? How many transects do you have to run across that entire population? I think I said 500 individuals. How many of those polygons or those individuals have to be transected in order to get that precision of 56%? What's the uncertainty of that 56%? I can guarantee you there's no way you're going to be able to hold that up with any sort of precision and accuracy to say that, yeah, this Dix field represents 56% and this kernel is 31%. So in summary, let's summarize all of this up. Your database, the NASIS database, contains estimated soil properties. It does not contain lab database. The component and the horizon tables are an aggregation of an extremely small set of point data that you've collected from a massive unseen population that you're assuming based on your landscape model. And so that data that you're collecting, you've collected it using various methods of analysis. And you have to weigh all of this and be aware of the level of uncertainty for all of that data that's been collected before you sit down and analyze this data and make decisions on how you're going to present this. And then when you do sit down and populate the NASIS data, you have to remember that you are only allowed to populate based off the lowest level of uncertainty of all of this data that you've analyzed, all of this data that you've collected and coalesced and analyzed. You have to use the lowest level of uncertainty. So that basically gives you a brief synopsis of the NASIS data and the way you populate this NASIS data. And please do not let me find you populating decimals in sand, silt, and clay and unreasonable percentages of precision in compositions. So take a look at this. Go back over it again if you need to. Give me a call, send me an email, and we can discuss it further. But the point is, NASIS data is an estimated soils database, and let's keep it that way. That's great. That's it.